So, in this video we are going to talk about the integrals of motion. The integrals of motion are certain quantities that won't change in time. It has sense to talk about integrals of motions if we are working inside a closed system, thus an insulated system. So, in a system with s degrees of freedom, we will have 2s minus 1 integrals of motion. So, some of them are quite important, and so they do have some names, and we are going to talk about them. The first one is energy. Let's see the conservation of energy. As we are in a closed system, we can say that the Lagrangian will have no explicit time dependence. So its partial time derivative will be 0. So the total time derivative of the Lagrangian should be in the form dt of L. So we will have the sum of the partial derivations according to the position times the time derivative of the position plus the partial derivation according to the velocities times the double time derivative of the position, so the time derivative of the velocities. But we can rewrite this in a different way. We can rewrite it as the total time derivative of this thing. So the derivative of the Lagrangian according to the velocity times the velocities. But now, by putting the Lagrangian on this side of the equation, we can rewrite it in this way. So now we see that this time derivative should be equal to 0. Thus, what we have inside this time derivative must be constant. And this is how we call the energy of the system. So we have seen that the energy must be constant in time if there is no explicit time dependence in the Lagrangian. This is actually both true if we are in a closed system or even if we have a time-independent field. So a not closed system with a time-independent field. Anytime we are in a system where energy is conserved, it's called a conservative system. And if there is a field that will conserve energy, it's a conservative field. And we will actually see this expression again in different situations, because it will be quite important. Another important integral of motion is the momentum. So, by imposing that after an infinitesimal parallel displacement of each particle in the system, the Lagrangian must remain constant. So, if I have an infinitesimal displacement that I will call epsilon, that is equal to the sum over all the particles of the infinitesimal displacement of the particle, and I want the Lagrangian to stay constant. So we can look how the differential of the Lagrangian will look like. It will be in the form of the sum over the particles of the derivative of the Lagrangian according to the displacement times the displacement. But now this, if I take this outside of the summation, it can become epsilon equal the summation of the time derivative of the Lagrangian divided the position equal 0. So this equation can have two solutions. One trivial one, if I have no displacement, so epsilon is equal to 0, of course the Lagrangian won't change. The other one, if this quantity is 0. But this quantity can be written in a different way. It can be written as the time derivative of the derivative of the Lagrangian according to the velocities. Of course, the sum over all of them. Now I left the notation of r and I used the generalized velocities. And I want it to be 0. So this is equal to this part here. At this point, if this time derivative is 0, this must be a constant, and this is the total momentum of the system. Now, we already seen this exact expression. In fact, we said that the energy of a system can be expressed as the sum of the velocity times the derivative of the Lagrangian according to the velocities minus the Lagrangian, but we now know that this is the momentum. Thus, what we get is the sum over I of the velocities times the momentum minus L. And actually, we will receive this expression when we will derive Hamiltonian mechanics. Then another interesting thing is that total force of the system, can be expressed as the sum over all the degrees of freedom of the system of the derivative of the Lagrangian depending on the position. That is equal to the time derivative of the derivative of the Lagrangian, of course the summation, depending on the velocities. So it's the time derivative of the momentum. But as the momentum is constant, this means that the total force of a closed system must be 0. So we arrive to demonstrate that the total force of a closed system is 0, and we had a shorter way to write energy, and we have seen that the momentum is an integral of motion. So the last integral of motion we're going to talk about is angular momentum. In this case, we are going to impose to the Lagrangian to stay constant after an infinitesimal rotation of the system. Thus, the displacement of a particle can be written, so for particle A, for example, can be written as an infinitesimal angle vectorial product, the position of this particle. That's actually a vector too. So the infinitesimal displacement can be seen as the vectorial product between an infinitesimal angle and a position. And in the same way, you can say that the velocity is the vectorial product of an infinitesimal angle times the position, vectorial product, the position of the particle. And we are going to impose the Lagrangian not to change. The differential of the Lagrangian can be expressed as a sum over the particles of the derivative of the Lagrangian depending on the displacement times the displacement plus the sum over the particles of the differential of the derivative of the Lagrangian depending on the velocity times the infinitesimal velocity displacement. And we want it to be 0. After some math from this, we can come on to say that the time derivative of the sum of the particles of the position of the particles, vectorial product, the momentum of the particles must be 0. Thus, this quantity must be constant in time. And this is how we define our angular momentum. So the angular momentum is an integral of motion. That I forgot to say during this video, why we can't assume all these things like that the Lagrangian won't change in time. Why the Lagrangian won't change in time, and not only because it won't have a explicit time dependence, so that we always assume it that the partial derivative of the Lagrangian is 0, but also that the total derivative of the Lagrangian is 0. This is possible because we are considering a closed system in an inertial reference system. So an inertial reference system is a system that doesn't have an acceleration. So it can move in a straight line using with a constant velocity, but it can't accelerate. Thus, we should, as it doesn't accelerate, the Lagrangian can't have any explicit time dependence, so the partial derivative of the Lagrangian should be 0. But as the system is closed, nothing can change the Lagrangian from the outside. So actually the absolute time derivative of the Lagrangian should be 0. While the reason why you can translate the whole system and keep the Lagrangian constant, or rotate the whole system and keep the Lagrangian constant, is again because we are assuming homogeneity of space, and we could do it because we're working in a inertial reference system and of an isolated system. So actually, if I translate the whole system, I will have the same interactions that I had in the previous system, because as I translate or rotate it, I won't change the relative particle-particle interactions and the relative particle-particle distances. And as it is isolated, the absolute position of particles in space won't influence the Lagrangian. For example, if I had some kind of field, even a very simple central field or any kind of field, then of course the absolute position respect to that field could change the Lagrangian. But in this case, you wouldn't be in an insulated system anymore, in a closed system anymore. So for example, if I am near to a wall, if I completely rotate, my Lagrangian could change because I would hit a wall.